So at any stage, if we try to find out the specific conductance of this reaction, then this will depends on the molar conductivity of sodium ion, the concentration of sodium ion, molar conductivity of hydroxide ion, the concentration of the hydroxide ion, and molar conductivity of the acetate ion. Okay, so sodium acetate also depends on the molar conductivity of acetate ion and concentration of the acetate ion. So sodium ion is actually same for there is no change for the sodium ion, because this sodium will go here, so there is no change of the sodium ion. Okay, so we know what is the concentration, molar ion concentration, but what is the molar conductivity? This one actually basically depends on the concentration, depends on the size of the ions. How? Suppose for the hydroxide ion, okay, the number of hydroxide ion is here, and what will happen if you suppose you have a sodium hydroxide? As I said, we will add a lot of the sodium hydroxide ion. Okay, so we will add a lot of the sodium hydroxide ion. Why? To convert it to the first order reaction, because the first order reaction, the equation is very simple. The first order reaction equation is very simple. So we convert it to the first order reaction by using much more excess amount of the sodium hydroxide. Okay, so we have added this we normally add 20 ml of 0.5 molar sodium hydroxide. So here we will add very little amount of the acetate ion. Then what will happen? Acetic acid ion. So ethyl acetate. So what will happen? This ethyl acetate will react with the sodium hydroxide and will form the sodium acetate and ethanol. Okay, a lot of the sodium hydroxide will remain unreacted. Okay, a very few amount of this will react with the sodium hydroxide. So this conductance, whatever the conductance at the beginning will be only for the sodium hydroxide, right? After the reaction, the conductance should be for the sodium hydroxide as well as for the ethyl acetate. But the problem is that molar conductivity. The molar conductivity mostly depends on the size of the ions. The sodium ion and hydroxide ion both are very small, right? But this hydroxide ion, when reacting with the sodium ethyl acetate, then it is forming the sodium acetate ion. This sodium acetate ion is very big. It cannot move. Okay, so it cannot move. So that's why the molar conductivity should be decreased. So that's why what is going to happen with when you are going to add the sodium ethyl acetate, then the conductivity is decreasing. Okay, so at the beginning it will decrease very sharply, but after 15 minutes around, okay, you will see that it is not going to decrease that much. Okay, then and after sometimes there will be a plateau actually. There is no change of the conductivity. Okay, so by using these techniques, we will try to use this technique to find out the unknown concentration, half-life time, rate constant, and activation energy. Okay, so determine the concentration of the unknown. It's very easy. So what we normally do, I will give you the data for this. Okay, you will get the data for this. I'll give you data. There will be some blank and you have to fill it up, all those blanks. So first what we will do, we normally use at constant temperature. Since we are going to find out the unknown concentration, we will have to use the constant temperature. If we don't use the constant temperature, that can be changed. So that's why the first reaction we are going to use the temperature constant. So at the constant temperature, keep the temperature constant. At the constant temperature, we will take 1, 2, 3, 4, 5, 6 of the test tube. Okay, in 6 test tube, we will actually put it in the calorimeter, having the temperature same. It may be 20 degrees Celsius temperature. Okay, so after keeping it for 10 minutes, then the temperature will be around 20 degree. Will be around the temperature of the calorimeter. So then we will add 0.1 ml of acetate, ethyl acetate. In the first we will add, before adding we have to find out the conductance. So suppose before adding the conductance is 5000. I will give you in the data. Suppose for it is 5000. Then if you run it for long time, so and we will keep stirring the solution. You have to keep stirring the solution and you have to take the reading continuously for at least 15 minutes. Okay, because why 15 minutes? If the half lifetime is in between that's so you have to run it for the 15 minutes. Okay, so you got it 5000 and you also got the value here, all value you have here, and then after 15 minutes taking the data for 15 minutes continuously, and during that time you definitely need to stir it. Okay, and you keep it. Okay, you don't have to bother about that, you have to keep it, and then after 1 hour you will take the data again. Suppose after 15 minutes the data is around 2300. Okay, after infinite time you see that the is around 2000. Okay, so this is the after infinite time, that means the reaction is done, completed. Okay, so the initial value should be 5000. I will give you this data in your, so suppose the initial value is 5000, the after t half you will get it, so after infinite time if it is 2000. Okay, so the same way you are going to get the value for the 0.3 after finishing it. Then you have the another second test tube. Okay, second test tube. Then on the second test tube you are going to do the same thing, but this time you are going to add 0.5 ml. Okay, 0.3 ml. So 0.3 ml you are going to add, then you are going to get x naught and x infinity. So what will happen for the x infinity? So definitely that's this reaction, since the concentration of this is more, the amount of the ethyl acetate is more than the first one, so that's why this reaction will go a little down, isn't it? Okay, so the same way the 0.1, 0.2, this 0.9, it should go on this way. Okay, suppose this is for the 0.9. If it is 5000, this should be 5000 for all, but the end value that at the infinite time, this value will go decrease with the increasing of the amount of the ethyl acetate. So suppose for the 0.9 it is 1000. Okay, so this is called the x naught and this is called the x infinity. Okay, so this value you are going to put x naught minus x infinity on the y axis and concentration on the x axis. Okay, so if you do that, then you are again going to put the unknown. Okay, we will give you the unknown, and what will you do? You will get same the x naught and x infinity value. Okay, and from that value, suppose if it comes here, you can get the y equal to mx plus c, and from there you can find out the concentration. It's very easy, right? So you can get the concentration of the unknown by using the conductivity method. Now the second part. So normally this lab needs to do like in one day we actually finish this part, because you have a lot of waiting time. So if you take the data for 15 minutes, 15 minutes, 15 minutes, 15 minutes, 15 minutes, 15 minutes, so here almost you need like 150 minutes around. Okay, although 7, but you have to do wash it, these a lot of times, so like 3 hours normally goes. So here another thing, that is the determination of rate constant. Okay, so what is the determination of the rate constant? K. As I said, what is K? K is only the proportional constant, rate constant. K. So how can you find out? So here what we did at the same temperature, but here the second thing, why we will do at the different temperature by changing the temperature, but this one will remain same, 0.5 ml. Here we change the amount of the ethyl acetate, but here we will keep the ethyl acetate same amount, but the temperature will be changed. Okay, so if we do that, the same thing is very easy. So with the increasing of the temperature, what will happen? The increasing of the temperature, the number of moles will get more, number of particles will get the activation energy, so the reaction will go much more towards the product. right? Reactant will go much more towards the product. So we will have 15 minutes data for 15 minutes, 20 minutes, 25 minutes, 30 minutes and 35 minutes. Okay, and we will take 0.5 ml, 0.5 ml. So for 20 minutes you will get it from here, and other things you have to do it. So normally what we do, we give you some like different batches having the temperature, okay, constant temperature. One maybe with the water bath with 15 degree, another one is 20 degree, 25 degree, 30 degree, 35 degree. Okay, so different water bath will be there, and you have to put your sample inside with the test tube. Okay, with the test tube we are going to put it, and then in all of those, suppose for the 15 degree, first you will take that test tube and you have to put the 0.5 ml. So at the initially you will check the conductance value, and you have to continuously measure the conductance for 15 minutes. Then after 15 minutes you will keep it, because you have to take the value again after infinite time. So this is the infinite time, this is the T half. So here you have to find out the T half for this one. So how will you find out the T half? This is the 5000 and this is the 2000, as I said. So this is the 2000 and 3500 in the middle point. So from the 3500 you will extrapolate a line on the x-axis, and this is the time. This is the time. This is called the half-life time. So you are getting the half-life time. So there are two techniques to find out the activation energy. Rate constant K. So but if you know the half-life time of the reaction, it is very easy to find out the K. How? We know that T half is equal to 0.692 divided by K. Okay, so you know half-life time, you know 0.693, it's a constant value, so you can easily find out the K. How? K will go in this side, 0.693 divided by the time, like T half. Then you will easily get the T half of the reaction for the 15 degree. Okay, the same way you can get for the 20 degree, 25 degree, 30 degree, 35 degree. Okay, so you will get the T half and you will get the K. If you get the K and T half, you can easily get the ln K, ln K. Okay, so you get the ln K. So for here you see we are getting the actually rate constant for all the reactions. For all the reactions we are getting the rate constant. Okay, so we got the unknown concentration, we got T half, we got the rate constant. Now what? Now the activation energy we have to got. Okay, so how to get the activation energy? So according to the Arrhenius equation, the ln K is equal to E over RT multiplied with 1 over T plus ln Z. Okay, so you don't have to, this is the C, so you have to look at this one. So what is this? ln K you will get it from here. ln K value you will get it from here. So you are going to put all those ln K value in the y axis, and on the x axis you are going to put 1 over T value. Okay, so you have to convert this temperature into the Kelvin temperature. Okay, 1 over T. So Kelvin temperature, then if you put the ln K over 1 over T, then you will get a curve like this. So this curve is nothing but the minus E over R. Okay, it is not T. Minus E over R. Activation energy over R means, you know, this is the gas constants. So E over R. So here we know the value of R. Okay, whatever the slope you will get, we know the value of R. So you can easily find out the EA, activation energy, will be in the joule. You have to convert it to the kilojoule. Clear? So how, like all the calculation what will you do and the experimental theory is done. I am going to show you. I already explained how to do the experimental part, but still I am going to show you. It's very simple. In the